ਹੈਲੋ ਹੈਲੋ ਠੀਕ ਹੈ ਮੈਂ ਵੀ ਚੈੱਕ ਕਰ ਲਈਏ ਦੂਜਾ ਵੀ ਹੈਲੋ 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 हेलो हेलो
हेलो
हेलो हेलो
बोलो ना। हेलो हेलो
हेलो हेलो ਉਹਦੀ ਘਟ ਨਹੀਂ ਆਵਾਜ਼ ਹੈਲੋ ਹੈਲੋ
हेलो हेलो
ਹੈਲੋ ਹੈਲੋ
हेलो तो ये चक्कर तो लाइए कितने हेलो चलिए
हेलो
हेलो हेलो
ਬਿਲਕੁਲ ਕੋਲ ਲਾਣਾ ਪੈਣਾ
हेलो हेलो मैक्सिमम भी है हेलो 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 मेरे सामने हेलो 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 तो सही है हेलो
ਬਿਲਕੁਲ ਹੀ ਕੋਲ
हेलो 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 जब करने माइक पर नहीं पे जाओ तो अपना
हेलो
नेटवर्क एंड कैमरा लाइक
topics in molecular magnetism that we, my group, and others, including that of Professor Hundal, are interested in, and then move on to talk about how we as synthetic coordination chemists can start to look at some of their key properties. So I mentioned to you yesterday, then right at the very end, that there are a number of important applications of molecular magnets. One of those is spin crossover, okay, so shown here. And this is a type of coordination compound where there are at least two different spin states for the same transition metal center, and the ability to switch between one of those, high spin, to low. Very short summary, much larger calculations to be executed in significantly less time. This is an example specifically involving cobalt. Other metals are known, including iron, to a very large extent in this course, are so-called single molecule magnets. This again is an example with dysprosium, where again there are other examples known with different lanthanide, terbium, holmium, and erbium. And again, the way that you dial up the different property is to use a different type of ligand environment. So these are some specific examples which, taken together, highlight a number of general principles, which really boils down to the fact that ligand design is the key in this area. Okay? Smart ligand design allows different magnetic properties to be targeted. And this is where coordination chemistry really starts to grow in importance. So what I will do for the purposes of this course is tell you predominantly about the basics of the magnetism, and then focus specifically on single molecule magnets, what they are, why they might be interesting, in a way that a coordination chemist can understand. Okay, so that, if you like, is an overview of some of the applications. We'll move on now to a cutting edge application. I should say as well, by the time this course is finished, the lectures are being recorded, okay, but I'm quite happy to provide you with the slides so that you have the presentations yourself to look at when we're finished, okay? So if I'm going too fast for you to write everything down, don't worry, you will get the lecture notes eventually, that's no problem. Okay, so I've mentioned things called quantum computers, which we hear an awful lot about in the media. So traditional computer is based on a bit of information. Okay, a bit is a binary digit, 1 or 0, and that's how you encode your information. A qubit, or a quantum bit, is an analogous species based on a quantum device where you have a superposition of many different states, which allows you to do calculations faster. And when people talk about things like this, in principle it sounds like a fantastic idea. But the question is, how do you actually make one of these things? And if you can make it, can it be used more widely? So one of the themes that I think we'll come across when I'm talking about various aspects of molecular magnetism, is that temperature is a really serious issue, a big challenge for those of us working in the field to solve. It is true to say that in applications such short answer to that actually is yes. Okay, there's a company in Vancouver, Canada, who have manufactured a quantum computer known as the D-Wave 2X system. It is a quantum computer, and this type of thing uses all the types of technology that I've already talked about here, and by operating in an extreme environment, -271, you can use quantum algorithms to solve very hard problems. Okay, so things like factorizing prime numbers, cracking passwords, things like that. Computers such as this can do it. And they are used. Companies, organisations such as NASA, institutions that forecast the weather are investing in this type of technology. So it is really clearly very expensive, nonetheless. And I think when it comes to looking at problems like this, the main limitation really is your imagination. Okay, so can you overcome these challenges by thinking very carefully and perhaps draw some inspiration from Max Planck, who you know all about, who says, when you change the way you look at things, the things you look at change. Okay, so challenges are there to be overcome, okay, not to be frightened of. We will not focus so much on applications such as this, okay, but nonetheless it gives you some idea that these things are real. So the bulk of this course will focus on the specific application of molecular magnets, known as single molecule magnets, SMMs for short. SMMs as a field, I guess, have been around for more than a quarter of a century. The first results appeared in the early 1990s. And what it was found, to draw some classical analogies here, was that you can synthesize and characterize molecular systems that show the same bulk properties as traditional magnets, such as iron oxide, neodymium magnets, and things like that, which have been around for thousands of years. So this is interesting. You can get a molecule to behave in the same way as a classical atom-based magnet. So ferromagnetism, by definition, involves collective ordering across long ranges. Okay, so ordering across domains on the scale of hundreds or thousands of nanometers. A single molecule magnet shows exactly the same effect, but clearly the magnetic domain that you are working with is just a molecule, so only a few nanometers, many orders of magnitude smaller. So this kind of fits in with the general drive towards miniaturization of the technology, okay, but in a slightly different context than what you may be used to. So what single molecule magnets are, they are typically coordination compounds based on transition metals, or lanthanides, or combinations of those types of elements. So, they are molecules that they can retain their magnetization in the absence of a magnetic field. This is a very big difference to what you would get with a simple Curie paramagnet, where you place your transition metal complex in a magnetic field, the moments align with the field, and then as soon as you switch the field off, the moments just become randomly oriented. A single molecule magnet will retain this magnetization. Quite a big difference. So they show magnetic hysteresis, at least in principle, that it is due entirely to the properties of an individual molecule and not to interactions between molecules, which is a very different situation to what we had before. So, to try and put this in terms of a size context, what I have here are at least two things that you will be familiar with. Okay, classical permanent magnet that all of you have with you right now in the form of a mobile telephone or a laptop. Okay, the way in which these machines store and process information is to use magnetic particles, probably not based on magnets. We're into the realms of nanoparticles. Okay, so this is a microscope image of a cubic iron nanoparticle published some time ago now, but nonetheless you can see that there are many orders of magnitude difference in terms of the size, but nonetheless materials such as this show the same properties as bulk iron. Then if we keep going down the size scale, when we get to the very bottom here, so a single number of spins, or maybe a few dozen spins, we're in the realms of molecules. And this is where single molecule magnets fit into the size scale. Okay, so this is the oldest single molecule magnet, published in the early 1990s. This is the very famous manganese 12 coordination compound. I will be telling you a lot more about this later on, but nonetheless, you can see the dimensions of this thing are in the region of 1 to 2 nanometers, so very much smaller than what we've seen before. The key point is that the properties of this material here are analogous to this material here, but on a very different size ratio. So as things currently stand, everything looks good. But there is a critical difference in terms of certain conditions under which these materials function. Now, as you are well aware, magnets such as this function very the synthesis is critical, the structural characterization in terms of molecular structure is critical, and measurement of the properties is critical as well. But the really crucial thing is linking these different aspects together in the form of what we call a magnetostructural correlation. How do the properties depend on the structure? How does the structure depend on the way in which you make your molecule? So we therefore have a side. They have very large magnetic moments, much larger than anything you would get with a transition metal, and they also have so-called very strong magnetic anisotropy. Okay? That is to say, magnetization has a well-defined orientation, and I will tell you much more about that over the next few lectures. Okay, so choose out some idea. They use metals, and they also in terms of symbolize stages is critical. Okay, you have to make your material to develop design criteria in order to improve the properties. Because in order to improve the properties, design various lectures is in principle yesterday, if you understand the chemistry of alkali metals, okay, so lithium through to cesium, you can do lanthanides in terms of the chemistry, no problem. Okay, the principles are identical. Okay, so I am an organometallic chemist, and I guess our contributions to this field really rely on the role of organometallic chemistry in single molecule magnetism. So taking the basic principles, I'll go into a bit more detail with the organometallics, and then I'll show you how this links together with the magnetism. At that point, it will be important for you to stop and to reflect on the things that I've told you, hopefully with the outcome that you've learned something. So what we will do at this stage here is a problem sheet, which you will be provided with. This will probably be tomorrow morning, if not tomorrow morning, tomorrow afternoon, where you can basically work through the lecture notes, which I'll provide you with, and you can work through some problems on there. And in principle, if you find this okay, we can then move forward onto the next section, which is where we start to look at magnetism in a little bit more detail. So going through this very quickly, we'll look at some basic properties. We will put things in a proper historical context by talking about transition metals, the lessons we learned from that. Moving forward, we move on to look at some lanthanides. And again, we'll stop to pause on that with the second problem sheet, which will kind of combine together the first few sessions with some problems on molecular magnetism, some of which you'll find relatively simple, some of which are a little bit more challenging, but the idea is you can take away these problem sheets and work on them after the course is finished. Then we'll look at some specific examples in the form of case studies, which I will select from the recent literature. Okay, it's a very active topic in molecular magnetism right now, so there are many examples that I can choose. I will just take a few key examples based on lanthanides and on transition metals for you to look at in order to look at things in a little bit more detail. And then number 10 down here was the one that I think piqued a bit of interest in the audience yesterday. So rather than you just listening to me all week, it would be nice for me to listen to a few of you to reflect on some topics as well. So there will be some student presentations, maybe 15 or 20 people, okay, depending on how much time we have. And what I will ask you to do is something called a 1-minute lecture. Okay, so it won't be everybody, it will be a random selection of people. Some people are smiling, some people are looking very unhappy about it, don't worry. Nobody has to do anything, but I think you will find it quite useful, either as a presenter, okay, or as somebody watching your peers give a presentation. At some point in your lives, when you go for a job interview or something like that, or when you're actually working somewhere, you will have to stand up and give a presentation. Okay, so I think it's good practice for you to try and do something slightly different. So your lectures will be lasting 1 minute only. I will time them. After 60 seconds, I will make you stop talking, okay? Or at least the audience will make you stop talking. And the topic, what I will do is, just so that it's related to this lecture course, the people who will be chosen to speak will be given a specific chemical element, and you'll have 1 minute to tell the audience something exciting about that element that they may not already know. Okay? So the people involved in that, I think I have your details here, okay? So I will randomly select maybe 15 or 20 people from this list here. You will receive an email from me, okay? If you don't want to do it, just reply to say you don't want to do it. It's fine, I'll just choose somebody else. It's really no problem. But hopefully from an audience of this size, we'll get 15 or 20 people. It should be no problem. And then what you will have to do, the instructions will be in the email, okay? You can present 1 or 2 PowerPoint slides, no more than that, okay? 1 or 2. And how you introduce your topic is completely up to you, but you have 60 seconds in which to enrich your friends, okay? So that will be interesting for me to see how you respond to that, and hopefully interesting for you as a learning experience. Okay, so those people will receive an email at some point today. The selection process is completely random, by the way. I don't know any of you individually, so it's nothing personal if you don't receive the email. Okay. Then right at the very end, this should get us through to Thursday afternoon, I will present a standard research colloquium based on the work that my group does in Manchester, where we are and where we're going with the science and principle that should take us through to the very end of the course. Okay. So, in terms of what you need to know to get into this course, this was again mentioned in the course synopsis before you started here. It's important that you know a little bit about basic transition metal chemistry, how those metals interact with ligands, counting of electrons, the electron configurations, and a little bit of basic symmetry and group theory. Okay? Not too detailed in terms of the latter 2 points. If you want to read more about the chemistry, okay, not so much the magnetism, then these 2 books here, which I believe you have details all about, are particularly good for these purposes. Okay, how are we doing for time? Okay, good. So, we will begin then with an introduction to the chemistry and the key physical properties of the elements in the 4F series, which are of course referred to as the lanthanides. Start with a bit of terminology. When you look at many textbooks and other sources in the chemical literature, you realise fairly quickly that the elements we are interested in have a slight identity crisis. Okay? So the elements in the 4F do it completely at ease. Okay? And maybe about 10 years ago, that was the sort of thing that the Chinese were doing. These elements are critically endangered resources, so we have to be very careful how we use them. It's important for you to know about that. If you want to know more, you can do a quick Google search on the rare earth crisis, and this will give you more statistics and things like that, and you will see that there is a bit of a problem. So in terms of how they use the rare earth elements, in terms of pollution in the atmosphere, okay, obviously motor vehicles and other things are a bit of a problem there as well. Catalytic converters in car engines, so petrol and diesel fuels, contain a very large amount of cerium dioxide, which is used in converters, as well as other elements as well. Petroleum refining catalysts go very heavily on rare earth elements. Permanent magnets is a big one as well. So permanent magnets are the things I was talking about inside your electronic devices, clearly very small amounts, but actually the scale of these things increases dramatically. So for example, wind turbines for renewable power, each of these contains about 20 kilograms of neodymium. And if you think about how common these things are nowadays, that's a lot of neodymium. So neodymium is a critically endangered element, partly for this reason as well. Neodymium is also used in industrial magnets. You can see things on building sites, big magnets lifting things around. Rare earth elements with a very big part of that. Also samarium as well. In terms of decorative applications or glass and things like that, glasses and ceramics are a big deal as well. If anybody here knows it's very, very easily, it's very good to do that, but actually we need to think precisely about the impact it might have on the global supply of elements of this nature. So this is one thing that is relevant to what we're going to talk about. Okay, so where do they come from? Well, clearly they're all naturally occurring, apart from one of them actually. But the existence of the lanthanides was predicted by these two here. This is Henry Moseley, who was British, Niels Bohr was Danish. And these two between them predicted the existence of 14 elements with atomic numbers ranging from 58 to 71. Okay, this was the fourth series of elements, and they predicted that these elements should have 32 electrons in the so-called fourth quantum shell. This you'll recognise as slightly outdated technology than what we know about atomic structure nowadays, but what they said for these elements, and what is different to the preceding elements, is that 14 of these electrons should occupy the same subshell. And that subshell is the series of the 4f orbitals. Therefore, there are 7 4f orbitals. Okay, so these were quite interesting characters as well, and reassuring for people like me, and perhaps like you as well. Obviously, their work as physicists essentially laid some of the foundations of modern quantum theory, and reassuringly, Niels Bohr said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet, okay? Which is good, because I don't think I understand it. So, in terms of the lanthanides, what we want to do is to try and build up a picture of their electronic structure. First by talking about the atoms, and then taking these atoms and placing them in a realistic chemical context, and then using that chemical context to look at coordination chemistry and designing ultimately molecular magnets. So we'll start with the basics and we will build up a picture of the complexity. So, when I teach this course to the students in Manchester, I'm giving you much more detail than they would ever have, by the way, but when I teach this course, one of the things I ask them to commit to memory as a fact is that the general electronic configuration of a lanthanide element is a xenon core, 2 6s electrons, and a variable number of 4f electrons. Okay, that is a critical fact we must commit to memory moving forward. Okay, so that is the general trend. Of course, a general trend must have a few exceptions because that's how trends typically work as well. And the 3 that you need to know about are lanthanum, gadolinium and lutetium. Okay, they do not fit this general trend for reasons that I will talk about in just a second. Okay, so here they are. These are the lanthanides. Now, you all have your own reasons for wanting to attend these lectures. One of the things I would like you to learn as a result of this course would be, if you are presented with the chemical symbol for each lanthanide, you actually know what the name is. Okay? Based on experience teaching this course in the UK, a significant number of students have no idea what the name of the lanthanide is based on the chemical symbol. It's not so difficult to learn with a bit of practice, I don't think. But here are the names, so we'll go through them just for completeness. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. Okay, maybe slightly exotic sounding names, but nonetheless they are real, so please do try and learn. Here we have the details of the configurations. So lanthanum, as I mentioned, strictly speaking, is not a lanthanide because it does not have an incomplete F shell, but it is a rare earth element, so that's okay. If we look at cerium, I said this is the one with an unusual configuration. You can see it does not fit this general trend that I talked about on the previous slide. It has F1, S2 and a D electron, so that's different. Then we can see the general trend starts at praseodymium, S2, F3, S2, F4, F5, F6, F7, all fit the general trend. Then we get down to gadolinium here as well, and this one is slightly different. Okay. It could be F8, S2. Okay, that's a real effect for sure. Terbium, the general trend starts again, and you can see as we move through it all the way down to terbium, things are starting to behave themselves. By the time you get down to lutetium, you now have no choice, okay, because the F shell is full with these. Okay. The only one we haven't talked about in detail is cerium. Okay, I'm going to save that for the workshop problem sheet for you to have a think about tomorrow. Okay. So, here is the electronic structure of the lanthanides in a little bit more detail, in the form of something called radial distribution functions. Okay, you'll be familiar with electron density, wave functions in particular orbitals. The radial distribution function gives you an idea of how the electron density varies with distance from the nucleus, taking into account certain effects. So, what we have on the same plot here are the lanthanides, which are the dashed lines here, so 4F, 5D, 6S, plotted for comparative purposes against the actinides as well. These are the solid lines. We're only going to talk about actinides a very small amount, okay, so we're not going to focus too much on those. But you can see then for the lanthanides, the 4F orbital, okay, the maximum in this radial distribution function occurs at a very close distance relative to the nucleus. Okay, and then it dies away pretty quickly. What this is telling you is that the 4F orbitals are really quite close to the nucleus. Okay, they're really relatively contracted, much more so than 5F. And of course, as we increase the principal quantum number from 4 to 5, the orbitals get bigger and they expand a little bit, and by the time you get down to 6S, they're actually a relatively long distance from the nucleus. So hopefully, this doesn't surprise you too much because you know all about principal quantum numbers from previous lecture classes. Generally speaking, as n increases, the orbitals get bigger, and this is telling you exactly what. So each of these is represented by a well-defined mathematical function, which I'm not going to show you today. But what you can see, for example, with the 5D orbital, if you can just spot this down here, the wave function kind of goes up and then goes down and reaches a value of 0 at this point, which corresponds to a radial node. Okay, there's one of those. When you look at 6S, there's a radial node here and also here. So there are two of those, and many more down here as well. The 4F orbital, on the other hand, you can see, does not have any radial nodes, and that is a key property of the 4F orbital, which we will come back to. Okay. So why is the electronic structure of a lanthanide set up in the way that it is? So we can try to conduct a thought experiment here, okay? This may not be the way that nature does it, okay? Nature obviously takes the path of least resistance, but nonetheless, for conceptual purposes, we can say, okay, maybe the electronic structure builds up like this, which will give us an insight into how the electrons are subsequently lost, and then how the chemistry happens. So try to imagine a situation in which we consider gradually filling the valence orbitals of a lanthanide atom with electrons. Okay, so you are an electron approaching a lanthanide nucleus. The first orbital to be occupied is the 6s orbital. Okay, and this is because the radial distribution function for a 6s orbital has a non-zero value, is non-nodal at the nucleus. This means if you are an electron, you can interact with the nucleus much more strongly, which is good for so many reasons, including electrostatic. As you move across the lanthanide series, Z increases, the atomic number increases. So if you are an electron orbiting a nucleus and you experience an increase in the positive charge, everything starts to shrink a bit because of the stronger electrostatic interactions. Okay? This is a principle that applies throughout the periodic table. So everything contracts slightly, but the 4F orbital contracts at a much faster rate simply because of the much lower value of the principal quantum number. Compare 6s to 4F, there's a difference of 2 in the principal quantum number. That's a very big difference, actually. So as we move across this lanthanide series, the energies of these 4F orbitals drops off really rather dramatically as a result of the increase in temperature. As a result of that, although we populated the 6s orbital at the very start, actually by the time we start to move across this series, 4F is inside 6s, and 6s is relatively extended relative to the nucleus. 6s is highest in energy. So conceptually, this is how you can build up the electronic structure of a 4F F species. So, in a normal chemical context, you do not do chemistry with lanthanide atoms. Okay, you obtain a common chemical precursor which you buy from a regular supplier, and it comes in a certain form. Okay, you probably know what that form is, but we'll build the picture up slowly anyway. So, lanthanides, being metals, form from cations very readily, but they typically form a specific type of cation in the vast majority of cases. So if you place a metal atom near a atom that can potentially become a ligand, you will oxidize your metal atom to form a cation. When you do that, you lose both of your 6s electrons, and you lose them first. Okay, you lose them first because they're occupying orbitals that are relatively extended. But in principle, you can just keep losing electrons. Losing them until you reach such a stage where the energy required to remove further electrons is simply too much to be offset by the formation of chemical bonds. And for lanthanides, in 99% of cases, after losing 2 6s electrons, actually, you typically only ever lose 1 4f electron. Okay? That is the situation that nature presented. Okay? That means, in terms of doing real chemistry with lanthanides, the oxidation state that we are predominantly concerned with is lanthanide 3+. Okay, this you already know, I guess, from basic chemistry, but this is the reason why. Because why is that? And what does it mean? So we can do a compare and contrast with transition metals, okay, which is an area that you have more familiarity with, I think. If you look at elements like manganese and iron, they have oxidation states varying across a bewildering array. Okay, so iron, the maximum possible oxidation state is +6. If you treat it correctly, you can do +5 and +4. +3 and +2 are extremely common. +1 is not unheard of. 0 is known, and there are also negative oxidation states. And something similar occurs for manganese as well. For lanthanides, on the other hand, we're limited. One oxidation state, which is lanthanide 3+. So again, I will mention here that there are a number of key facts that you need to take away with you from this course, and one of those lanthanides have a strong preference for the +3 oxidation state, dominating the chemistry. Okay, so if you look at the radial distribution functions for the post-lanthanides, cerium I said is one of the usual ones. 6s electrons go away first because they are on average further from the nucleus, so here most of the time, and they are shielded slightly by the other electrons. I will come back to this in a little while. Obviously the loss of an electron from an atom requires you to put energy into it, okay, which is uphill. Okay, you have to work to do that. So where is the compensation to take you down the other side? Well, clearly it's the formation of a chemical bond. So it's a balance between two factors. To get electrons out of to put energy in, and to reach a stable species that is actually more stable than the atom you started with, you have to form a series of chemical bonds. So there comes a cut-off point beyond which the energy required to remove the electrons is not, if you like, offset by the energy you form through chemical bonds. And for lanthanides, it turns out to be only 3 electrons. So, 6s is no problem, 2 electrons out, form some chemical bonds, you can compensate for that, no problem, exothermic. But, we must remain mindful of the fact that as we are losing these 6s electrons, as the lanthanide is progressively ionized, positive charge is building up on the ion. All of these radial distribution functions contract, they shrink. Because they shrink, they become closer to the nucleus and they are relatively stabilized, and the 4f orbitals experience this to a very significant extent. So you can put some energy in to get rid of 1 4f electron, form some chemical bonds, and everything is okay. But if you try to go beyond that and remove a 4th electron from the lanthanide, the amount of energy required is simply too much for it to be chemically realistic. Again, this is the reason why lanthanides, in the vast majority of cases, stop at the +3 oxidation state. Okay, so to give you some numbers to support that argument, which was presented in a very general sense, we'll look at one example. We'll take gadolinium. So what we have here are some numbers for ionization energy 1, 2, 3. And you can see for gadolinium, the sum of the first three ionization energies is this, 3,750 kilojoules per mole, for the sum of the first three. When you look at ion species, which is this, counting electrons is important, especially for magnetic properties. So it's very important for you to know that here lanthanides do actually have something in common with transition metals, which is when you are talking about the electronic configuration of a lanthanide 3+ cation, it is always 4f something. Okay, never 6s to 4f something or 5d something, 4f something. Okay, it's always solely composed of 4f electrons. It's absolutely critical that you retain it to be so. Okay, so we've done the ionization. We have our cation with this configuration as well. The impact of that is that the 4f orbitals now, as we've started to ionize our species, they were already very contracted. Okay, I showed you that here. They were already very contracted. As a result of being ionized, they really are now very, very contracted indeed. Okay, they're in fact inside the 5s and the 5p orbitals, okay, which are full. The 5s and the 5p series in the periodic table come before the lanthanides. That is a closed shell species. So your 4f orbitals are inside the closed shell. What does that mean? It means that they see very little of the environment around them. Okay, they are deeply embedded within the cation. This is a critical difference with transition metals, where you're used to thinking about ligands as sigma donors, pi donors, even pi acceptors, which inherently involves overlap of orbitals. Okay, in an ionic system, the bonding is electrostatic. The key word there is static. Okay, there is no overlap of orbitals in a system that has electrostatic bonding. So that's very, very different to transition metals. Where it is more familiar, however, is when you're talking about the chemical bonding in compounds of S compounds, lithium, sodium, potassium, rubidium, cesium, where the bonding is also ionic. So this is why I said at the very start, if you can understand the chemistry of S-block metals, you can understand the chemistry of the lanthanides, because the bonding is ionic. Okay, so this is hopefully a connection you can make with what I'm telling you now to what you already know from the previous lecture courses. So this has a huge number of implications in terms of the coordination chemistry, which we will talk about. I should also insert here kind of an insurance policy. Okay, the bonding is not 100% ionic. Okay, there really is no such thing as 100% ionic. Okay, there is a small covalent contribution, but there has to be. Okay, so nonetheless, you wouldn't go ahead and distort the argument based on the covalent ground. You would say ionic, and that would be fine. The reason this turns out to be significant is at low temperatures in particular, and this can also be particularly important for the magnetism in terms of things like crystal field splittings, which we will come back to in a bit more detail. Okay, let's look at this slide and also the next one as well. So we have lunch at 1 o'clock, is that right, Peter? So I will just present this slide here, and then we'll stop. Okay. So, what I haven't told you about yet is what 4f orbitals actually look like. Well, here they are. You can see that their structure is rich, certainly compared to what you would get with an s orbital or a p orbital. There are some similarities with d orbitals, I think you will agree, but they also have their additional features. So 14 f electrons, we're expecting 7 f orbitals, which is indeed the case. And up to this point that sounds quite simple, but actually they can be represented in two contrasting ways, just to complicate matters significantly. There is a general set of f orbitals and a so-called cubic set. The cubic set is applicable to high symmetry environments, the general set to everything else. What does that mean? I will tell you later. If we take the general set, you can see a number of features. Okay, so the labels themselves look like this. You probably will never be asked to draw an f orbital, by the way. I think it's important at least that you know what they look like. So fz cubed looks a little bit like a dz squared orbital with additional structure. Fyz squared, fxz squared look a little bit like dxz and dyz with additional structure, so on and so forth. But you can see down here with fxyz there are 8 different lobes in the same orbit. The precise details of these orbitals we're not going to dwell on a great deal. But what you can see, first of all, is that they are anti-symmetric with respect to inversion. This is different to a d orbital, which is symmetric, but the same as a p orbital, which is anti-symmetric with respect to inversion, different to an s orbital, which is symmetric with respect to inversion. So if you look at s, p, d, f orbitals, the symmetry goes G, U, G, U. They alternate like that, so the f orbitals fit in that trend. What you can see very clearly is that they have a very strong angular dependence. If you were to look at the wave functions for these orbitals, the angular component would be very big. This is pretty obvious, okay? They're a long way from being spherical. In terms of certain properties, okay, they have nodal structure, so wave functions have an angular part and a radial part. There are 3 angular nodes. This means that when you look at the wave function, there are 3 angles at which the value of the wave function drops to 0. So if we take, let's just say this one here as well, you can see there is a node going through here, one through there, and also one through there, that's 3. This one here, you can see there's one going through there. Here there is what we call a nodal cone, okay, so cone-shaped, and also one here as well, so that's 3. And if you want to work through the others, you can see that this is the case. They also have 0 radial nodes. That means that if you look at the radial part of the wave function, there is no value of the radius at which the wave function drops to 0. What that means is that the radial distribution function should go up like this and down like that, which you've already seen. So the question is then, does this actually matter in terms of the lambda-wise? Do you need to know about this in terms of the overlap of ligand orbitals? No, you don't, because based on what I told you here as well, these orbitals are so buried within the ion that they don't overlap the ligands, so the shape of them doesn't actually matter, okay, in terms of the chemistry. Where it does matter, and where it gets a little bit more complicated, is when we're talking about magnetic anisotropy, because I think you will agree they are highly anisotropic orbitals, and we will talk about them in more detail. So what I've just told you there about the 4f orbitals also applies to the 5f orbitals, with the slight difference that 5f orbitals have one radial node and one zero. Okay, so I stand between you and your lunch, so we will stop there and we will pick up in the lecture after lunch with the lambda item traction and talk a bit more about chemistry. Thank you. Yes, as I mentioned yesterday, if you do have any questions, you can. If you have a burning question during the lectures, please just raise your hand. It's no problem at all. But otherwise, any time during the day, please just ask me. Thank you.
You'll be giving them the topics